everybody. Thank you for joining us today. I will briefly say a few words about our seminar for those of you who are with us for the first time. Our seminar includes presentations from leading young academics in mathematics from around the globe. It is accessible to a broad audience, no matter the field. And our main idea about this seminar is to inspire the upcoming generation of young mathematicians. Seminars are held online every first Thursday of each month. And now I give the word to Christina, who will tell us more about today's speaker, Tom.
Hi, welcome to everyone. Today we have Tom Hutchcroft. Tom is a professor of mathematics at the California Institute of Technology. He served previously as researcher at the University of Cambridge and Trinity College, and he obtained a PhD in 2017 from the University of British Columbia. Tom's research interests lie mostly in discrete probability, with additional focus on mathematical physics, group theory, ergodic theory, metric geometry, and combinatorics. Tom has obtained competitive grants, such as the Packard Fellowship for Science and Engineering. Some of Tom's awards include the one given by the European Mathematical Society, and one for an outstanding paper by the Journal of Mathematical Physics. He has an extensive list of publications in prestigious journals, such as Annals of Probability. He's associate editor in several journals, including probability theory and related fields. He also organizes online seminars, as we do, on both Bernoulli and dependent percolation processes. So I encourage specialists in the area to follow them. And well, without further ado, it's a pleasure for us to have Tom today. Sorry, apologize about that time, because now in the USA is very, very early, but thank you. And he will talk on the effect of spatial structure on phase transitions and critical phenomena. The floor is yours.
Great, thank you very much. Thanks for having me. Thanks everyone for coming. So as my title slide says, I'll be talking about the effect of spatial structure on phase transitions and critical phenomena. So of course, the first thing I have to tell you is what I mean by that. And I want to take a very sort of vague and broad view of what I mean by a phase transition. So what you should have in mind is you have some system that has a large number of components that all interact with each other in some way, and where this interaction is governed by some parameters that you can vary continuously. So you could imagine the temperature or the pressure, something like that. And a phase transition occurs where varying these parameters through some special value causes some kind of abrupt qualitative change in behavior of the system. So often mathematically we'll work with infinite size systems, which are so infinite volume limits of finite systems, and we'll actually see discontinuous changes in behavior at the phase transition. Okay, so of course, you know, there are many examples of systems undergoing phase transitions that you'll be familiar with from your everyday life, like boiling water in a kettle. There are other, but there are many more examples that you may be less familiar with. So even within physics, there are other examples such as the phase transition in ferromagnets. So if you have a piece of iron at room temperature, it's ferromagnetic, meaning that if you expose it to a magnetic field, it will become magnetized. You know, a piece of iron can stick to a magnet. That is actually no longer true of hot iron. So this is something that was studied in a lot of detail by Pierre Curie in his PhD thesis, actually. So he found that there's a phase transition at what's called the Curie temperature, where, again, iron at room temperature is magnetic, but hot iron is not. So of course, eventually the iron will get so hot that it melts. That's a different phase transition. But there's also a phase where it's still solid, but is no longer magnetic. Okay. So that's another example from within physics, but of course there are many other examples from outside physics too. And, you know, so one basic example that, you know, many of us were more familiar with than we would have liked to have been a few years ago is about diseases spreading through a population, right? So in that case, there's a parameter which is called R0 often, which is the expected number of people that each infected person infects. And when this is bigger than 1, the disease will spread rapidly through a population. When it's smaller than 1, the disease will die out quickly. And when it's equal to 1, complicated things will happen, as we'll come back to. Okay, there are also phase transitions occur in the computational average case computational complexity of combinatorial optimization problems, in economics, in like the behavior of financial markets, and formation of traffic jams. We basically now know that any large complex system, or almost any large complex system, it probably undergoes some kind of phase transition. It's sort of a generic behavior in that sense. And moreover, the mathematics underlying these phase transitions, why they happen, what happens around them, have a lot in common throughout all these examples. So you can kind of study phase transitions through the lens of a mathematician. Okay. Now, in my title, I didn't just say phase transitions, I also said critical phenomena. So what do I mean by that? It turns out that many systems, when you tune them exactly to the point of phase transition, they exhibit very interesting, often fractal-like behavior. So, for example, this picture was made by Jason Miller. It's something related to critical percolation in 2 dimensions. So I'll come back to talking about percolation more soon. And you can see you get these sort of very geometrically interesting sets in the plane. They have these very fractal-like boundaries between them, all this kind of thing. So, in fact, the phase transitions we're most familiar with in our everyday lives, like water boiling and so on, these actually don't exhibit this kind of rich critical phenomena, but many systems do, and this is one of the most interesting things to understand as a mathematician. It's also very hard. Okay. And as a sort of spoiler for what I'll say in more detail later, it turns out that these things are quite well understood now in 2 dimensions, 2-dimensional systems, and in high-dimensional systems, and they remain very difficult to understand in between that. So in particular, 3 dimensions and 4 dimensions are usually the most physically relevant. Sometimes 2 dimensions is relevant, but these remain very hard to understand. Okay, so an additional feature of phase transitions and critical phenomena, which is more like a sort of meta conjecture, and actually it's something we're able to prove in only vanishingly few cases, is the phenomena of universality. And so the idea of this is that the exact behavior of these systems at and near their point of phase transition should not be very sensitive to the exact details of how you define the system. Okay, so later on I'm going to be talking about percolation, which means it's a model of like a random media where you flip coins to decide, some sites are open, some are closed, and you want to understand the connectivity properties as you move around. So part of the idea of universality would be it shouldn't really matter whether you do this, with edges on the square grid, which is on the left, or with actually the squares on the square grid, which is on the right, or on a hexagonal grid, or if you had some randomly placed ellipses that have continuous symmetry. These should all have, not that we can prove this, but these should all have the same kind of large-scale behavior at and near their points of phase transition. Okay, so this, and again, this is something we really don't know how to prove except in a small number of simple cases, like for simple random walk, for example, where these things are very classical. Okay, so one thing this is related to is the idea that at points of phase transition, systems should become at the large scale limit. So when you zoom out and look at them on a very large scale, they should get more symmetry than they started with. There should be emergent symmetries. So you can see in these square grid models, you only have symmetry under 90-degree rotations, right, in the discrete model. Whereas in the one with ellipses, you have a full, 360 degrees, whatever, however many, whatever rotations you want to apply, it's fully rotational invariant. And what we believe and can prove in, again, a very small number of cases is that when you zoom out, you actually get more symmetries than you had initially in the limit, including, for example, full rotational symmetry for the square grid. Okay, so one really nice thing, about this is that there's this thing about physics studying spherical cows, right? That you start with the real problem, and then you add all these simplifying assumptions, and it no longer pertains to reality. And of course, the models that we study in statistical mechanics tend to be vastly simplified compared with the behavior of real systems. But the phenomenon of universality says that for many purposes, this actually shouldn't matter, because as long as you get enough of the details correct, and that often means having some appropriate kind of symmetry or something like that, then you should actually be correctly understanding the physical phenomena, at least as they pertain to these universal things. So not every aspect of a system is universal. So, for example, all these systems will have, like, if you think about, they'll often be like the temperature where the phase transition occurs. The value of that temperature will be highly dependent on these microscopic details, but the behavior that you see at the critical temperature should not. Okay, so I've just been saying about how, the exact details don't really matter, but the really important thing is that dimension is really important, okay? So, here I was talking about how all these different two-dimensional percolation systems conjecturally should have the same behavior, but they won't at all have the same behavior as a three-dimensional system, and a three-dimensional system won't behave like a four-dimensional system, and so on. Okay, so what would we like to do as mathematicians? So one thing we would like to do is to try to construct and ideally describe continuum limits of these critical systems. So, the discrete things are just a mess. What we would really like to be able to do is say, okay, well, you take the lattice spacing to 0, you try to recover some kind of continuum theory, and then either prove that it exists or actually be able to describe it, say something about it. Okay, of course, that's a very mathematician's take on these problems, maybe, and but the hope is that by having descriptions of continuum limits, it actually is very helpful for understanding the systems. Often the continuum theories you get may be much more tractable. I mean, that certainly has been the case historically for the ones we've been able to construct. And so it's not just an abstract problem about proving that limits exist. The limits are actually very useful for understanding the systems. Okay, and related to this is developing a robust theory of universality and emergent symmetries. And again, all of these problems, I'd say, are extremely hard, particularly in intermediate dimensions. So, but I'll come back to say more about that later. Okay, and the problem is, these are like the grand goals of the program, but in reality, there are much more basic things that we don't understand first. So, but it's good to keep some lofty goals in mind. Okay, so let me give you a basic example of what I mean with this stuff about taking continuum limits. So the most classical example of this in probability is random walk converging to Brownian motion. Okay, so what is a random walk? It's a process in space, and you could define it on a grid, for example, where at each step you just randomly move, let's say, up, down, left, right, uniformly at random, independently of everything you've done in the past. Okay, so you can think of this, if you like, as giving you a random function, and you can even think of it as a random continuous function if you want it, by just linearly interpolating between the steps. Okay, and it turns out that you can meaningfully take the limit as the lattice spacing goes to 0. Okay, so the way you have to do this is you scale time by 1 over n, and you scale space by 1 over square root n. Okay, so this the sort of non-obvious scaling you have to do for time versus space. And this 1 over square root n, of course, is related to the central limit theorem, right? So the central limit theorem tells you that if you have a sum of n IOD random variables with finite variance, then, and you divide by root n, then it will converge to a Gaussian, right? To a standard normal if you cancel out the variance. Okay, so Brownian motion is like the function version of a Gaussian, right? It's like the continuous function version of a Gaussian. So if you look at the random walk at a particular time, it will converge to a Gaussian. The Brownian motion is the limit of the random walk as a function. Okay, and you know, Brownian motion, well, I guess it was originally something observed by Brown, who was looking at pollen through a microscope, and he saw it has this very irregular motion where it's sort of bouncing around all the time. I'm not sure actually mathematical Brownian motion is a good model of the original physical motion observed by Brown, although I think it is a good model for some other things where, so it was studied by Einstein as part of his Annum Mirabilis, where he had this year 1905, where he had special relativity, the photoelectric effect, and so on. And actually, for his purposes, the physical phenomena that you see Brownian motion was an important step towards towards having verifiable predictions of an atomic theory of matter. But anyway, that's another story. And mathematically, it was constructed rigorously by Norbert Wiener in the 20s. Okay, so what's the point of all this? Well, the point is not just that you can do it. It's not just say, okay, we have a discrete model, we can take limits of it. But Brownian motion is an extremely nice object to work with. So, you know, if you're interested in, and another setting where Brownian motion is used a lot is in finance, right? So modeling how, you know, stocks fluctuate and so on. And generally speaking, if you want to do computations, you're much better off doing them with Brownian motion than with random walk, because there are just many things that become much simpler in that continuum limit. Okay, and you know, another thing to notice is that this is one of these settings where we actually can prove universality, in that, you know, if you do the random walk with a different step distribution, like maybe you pick a uniform point on the unit circle around you each step or whatever, you'll still converge to Brownian motion, as long as you don't make very big steps, then you can get other limits. Okay, so let's go back to this thing about understanding critical phenomena. And here I just want to give you a very big picture of what's happened in the last 40 years or so. So as I said, there's basically two cases that we understand quite well, although there are, as always in any area of math, there are many more things we'd like to understand about the parts that we understand well too. So first of all, high dimensions was the first regime to really be understood. So in this case, there were, you know, big breakthroughs made in the 80s and 90s, in particular, using a technique called the lace expansion. And this is a fairly systematic way you can study lots of different models of statistical mechanics and analyze their critical behavior in high dimension. And basically, the reason high dimensions is easier is because the critical phenomena that you see actually become significantly simpler in high dimensions, and I'll talk more about that momentarily. And then more recently, but still quite a long time ago now, in the very late 90s and early 2000s, there were these breakthroughs, particularly by Oded Schramm, by Wendell and Werner, Greg Lawler, Stas Smirnov, and you know, over a sort of 5-year period or so, from like 1999 to 2005 or something, they really made a huge amount of progress on understanding these two-dimensional critical systems. And this is now something we have a very good theory, at least of the continuum theory. So there's still well, there's still many things to understand in the continuum theory too, of course. And it's also, there's not very many models where we can actually prove that they converge to these continuum limits, but at least the continuum theory we understand extremely well in 2D. Okay, so before saying more about that, I want to talk about some much easier things that I can actually explain everything to you. And these easier things I'm going to talk about, they're going to be, well, let's try and understand what, if we can analyze critical phenomena in systems with no geometry, okay? And basically what I'm going to argue later is that these the high dimensional things are eventually going to behave like things with no geometry. Like once you go to high enough dimensions, the fact that you have some finite dimensional geometry is basically going to become irrelevant. But let's start by analyzing some things that just have no geometry. So the simplest one is a branching process. Okay, so this is a very simple model for how a population grows or how a disease spreads through a population. It's something that is often studied in undergraduate probability courses, something you can very reasonably teach in an undergrad course. So how does a branching process work? You start with a single particle, and at each step, each particle so you have these generations, and at each generation, every particle in the generation has a random number of offspring. Okay, and they all pick how many offspring they have independently of all the other people in the generation. Okay, so you get this sort of random genealogical tree, right, of how this population is evolving through time. Okay, so there are a number of things that are quite easy to prove about this. So first of all, if you say that each particle has an average of R children, then the average, the expected number of particles in generation n, well, just using this independence and linearity of expectation and so on, you can easily prove that the expected number of particles in generation n is exactly R to the n. Okay, so in particular, you see that the expected number of particles in generation n decays exponentially when R is smaller than 1. It grows exponentially when R is bigger than 1. And it's always exactly equal to 1. In expectation, of course, that's an important point, when R is equal to 1. Okay, so one thing that's easy to see is, well, in particular, when R is less than 1, the expected number of particles alive in generation n decays exponentially. And, just by Markov's inequality, the probability that the process survives for n generations must decay exponentially. Okay. Now, a less obvious thing, which I don't have time to explain in this talk, but, again, this is something you can easily teach in an undergrad course, is that the process survives forever with positive probability if and only if R is strictly larger than 1. Okay. So in particular, what you'll see is when R is equal to 1, the expected number of people in generation n is 1. It's not decaying, but it's one of these settings where the expectation is actually much larger than the typical value of the random variable. It's like dominated by rare events, and in fact, the probability that you survive to generation n goes to 0. Okay, so that kind of repeats what I've written in this first paragraph. And in fact, what you'll see is that when R is exactly equal to 1, the probability you survive to generation n actually decays like 1 over n. Okay, so this does decay, but it decays much slower than when R is in the subcritical phase, when R is less than 1, where it decays exponentially fast. Okay, and then when R is bigger than 1, it just doesn't decay at all. Okay, now, although this model is very simple, it already exhibits these kind of rich fractal-like critical phenomena that I told you about initially. So if you condition on the process surviving for n generations, and then you look at, so you get this big, you take n, a very large number, you get this big random tree, okay? And then let's say, I'm going to try to take a limit of this tree. So this tree, I can think of it as a metric space, right? With the graph distance on the tree, and it has diameter n. So I'll rescale all the distances by 1 over n to make it like a diameter 1 object. And you can take a limit. Okay, so you have to define a topology on the space of metric spaces. That can be done, but I'm not going to get into it. And you'll get something in the limit that was constructed by David Aldous in 1991 called the continuum random tree. Okay, and this is a sample, of course, not really of the continuum random tree, just of one of these large branching processes generated by Igor Korczemski. And so this, again, this is converging to something called the continuum random tree. Okay, and again, the point of this is not just to say we can take a limit, so why not? Although that is part of the point, of course. But it's also that these continuum random trees are things that you can describe explicitly in terms of Brownian motion in a very nice way. This is one of the key observations of Aldous. And you can do computations with it, right? So, for example, one thing you have, and then you can try to transfer the computations you do in the limit back to the discrete and so on. So one thing, for example, this continuum random tree, I should say, you know, this embedding of it, you have to draw it in the plane somehow if you want to make a figure for your slide. But the embedding distorts the metric a lot, right? So in fact, this tree has as a metric space, it has Hausdorff dimension 2. So although it's a tree, it's in some sense a two-dimensional object. Of course, this embedding in the plane has Hausdorff dimension much less than 2. That corresponds to, in the discrete model, if you condition on having one of these very large trees, then the number of particles up to generation n will grow like n squared. Okay. So let's now look at a slightly more complicated example, which is the Erdős-Rényi random graph. Okay, so this is something many of you have probably heard of before. So it's a random graph where you have n vertices, and you independently include every edge with probability lambda over n minus 1. Okay, this particular scaling is chosen so that the average degree is lambda. Okay, so this model famously has a phase transition at lambda equals 1. So we're going to send n to infinity and then study what happens. That's closely related to the phase transition for branching processes. Okay, so you know, in the branching process, we were just saying, you know, does the thing survive forever or not? Of course, this is a finite graph. The cluster is never going to be infinite, so that's not the right question to ask. But we have the following sort of trichotomy. So if you fix lambda and then send n to 1, when lambda is smaller than 1, the clusters, and by clusters I just mean connected components of this random graph, when lambda is smaller than 1, this is the subcritical phase, the clusters are small. So the cluster at the origin will typically just have like order 1 many vertices, and the biggest cluster in the whole graph will be logarithmic order. When lambda is bigger than 1, you get a giant cluster. So this is like the analog of having an infinite cluster in the branching process. So the giant cluster has volume of the same order as the total number of vertices, order n. But the second largest cluster is still really small. And whereas at the critical points, when lambda is exactly equal to 1, here you get a behavior in between where the largest cluster has size of order n to the 2/3. Okay, so it's not giant in the sense, it's not linear, but it's much larger than it is in the subcritical phase. And there are kind of a random number of such clusters, or you should think, you know, the largest cluster is n to 2/3, the second largest is like smaller than that by a random constant multiple, third one again a random constant multiple smaller than that, and so on. Okay, and it turns out that you can also describe the full scaling limit of the Erdős-Rényi random graph. So let me just yes, okay. In a similar way to how you can describe the continuum random tree and so on. So it's something where you can take these clusters that you get, you know, their diameter is roughly n to the 1/3 in this case, and you can rescale by that and take a limit, and it's almost exactly the same thing as you get from the branching process. So this was studied by Aldous in 1997, who looked at the sizes of the clusters, and then by Adario, Berry, Brutan, and Goldschmidt in 2010, who looked at actually the geometry of the clusters too. And they showed that you know, you can take a scaling limit of say the largest cluster in the Erdős-Rényi random graph, and it converges to something which is almost this continuum random tree, but it has a random, first of all, its law is a bit different, but it's absolutely continuous. And then you add in like a random order 1 number of additional edges. So it's not quite a tree, but it's very close to being a tree. It's a tree plus a bounded number of edges, basically, that make cycles. Okay. So again, the point of these things is if you want to understand very fine properties of the critical Erdős-Rényi random graph, then the best way to do it will be to take the scaling limit, work with the continuum object where there's a lot more, it's much more suitable for doing exact computations, and then you can try to bring that back to the discrete. Okay, so now I want to introduce some geometry. So I'm going to be studying percolation, which we can think of as being like the Erdős-Rényi graph, but with some geometry introduced. Okay, so many of the things I'll talk about, they are either known or expected to be similar for many other models of statistical mechanics. Percolation is a nice one to focus on because, well, to start with, it's very easy to define. And often, actually, the way we understand other things is often we kind of compare them to percolation in some way eventually. So how does percolation work? So you just have some graphs. So in this figure, it's the square grid. I'm going to be doing bond percolation, which means I randomly choose to delete or retain the edges. You can also do site percolation, where you do the same thing with the vertices, or mixed ones where you do both. Again, by the universality principle, we don't expect there to be significant differences between these different setups. So you just have some graph, and you flip a coin for each edge. It has some probability of P of being heads. You keep every edge where you see a head. You delete every edge where you see a tail. Okay, and the jargon of the field is that the edges that you keep are called open, the edges that you delete are called closed, and we're interested in the geometry of the clusters, i.e. the connected components of the graph that we're left with. Okay. So the way we consider the phase transition in this model, so we'll be working with infinite graphs, partly because it's simpler. So we'll define theta of P to be the probability that the origin belongs to an infinite cluster, and you can think of this like the density of the infinite cluster. And the critical probability, PC, will be defined to be the infemal value of P where this is positive. Equivalently, PC is the infemal value of P where if you're larger than PC, an infinite cluster exists almost surely. The existence of an infinite cluster is a 0-1 event. Okay. The first basic theorem that makes the model interesting in some sense is that if you rule out one-dimensional examples, like if you do percolation on the line, you never get infinite clusters unless P is 1. But once you move beyond one dimension, you typically have that PC is strictly between 0 and 1, right? So in particular, if you work on a d-dimensional grid, PC is really strictly between 0 and 1. So you have a phase transition in the sense that up to PC, there are no infinite clusters, and then from PC to 1, there are infinite clusters. Okay, now in this particular example of the square grid, it's a famous theorem of Harry Keston from the 80s that the critical probability is exactly 1/2. This is ultimately a consequence of the fact that the square grid is its own planar dual. This is an important theorem, but it's something that you shouldn't take the wrong message from, in that the fact that you can compute PC in this example is highly atypical. So generally speaking, if you want to study critical percolation, for example, on the 3-dimensional grid, you're going to have to do it in a way that does not involve computing PC exactly, because it probably doesn't have any exactly expressible formula for it. It's probably a transcendental number and so on. Okay, so this is the fun part of the talk where I get to show you some videos. So I'm going to show you several videos of the percolation phase transition, and I should say these are all made by Niels Berglund. And if you enjoy these, you should go to his YouTube channel, because he has like literally hundreds of videos of statistical mechanics simulations. Most of them are not percolation, but he does a lot of really nice videos. And so this is going to be percolation on the, this is site percolation. Oh, sorry. On the, hopefully you can all see that okay. So as the video is running, so this is site percolation on the hexagonal grid. So it's like every hexagon is either open or closed, and the colors just indicate points that are in the same components. And you can see, if you're not too distracted by me talking, that as we cross a certain critical value, and in fact, in this case for site percolation, this is, well, we would normally call this site percolation on the triangular lattice. Really, it's on the dual of the hexagonal lattice. PC is again exactly a half, and you should see as P gets to a half, you'll start to see these much larger clusters emerging. And I think the video actually slows down a lot through getting close to a half, so you should look at the number of P in the corner to see that it is in fact a rapid change that you're seeing. I mean, it's going in slow motion through the rapid change. Okay, and you can see, let me skip to the next slide because I think I've got a, oops. Okay, so this is with a very fine grid. So we should see very suddenly that big structures begin to emerge. And again, the timing is going to be slowed down. Yeah, the colors just, it's just each cluster is colored at random so that you can see what the clusters are. I don't think they mean anything beyond that. Although I may be wrong. It may be that the clusters actually denote size. So we'll see if I try to pause it at the right moment. Oops. Well, okay, you can see when P is very close to a half, the clusters have this very intricate fractal-like structure that you can see, right? They have these big holes. They have, the boundaries have all these sort of fjords and things like that. And these are all the kind of things that we would like to understand. Okay, so, and then what, you know, once you're significantly above 1/2, like here we're at 0.53, right? Here you have like one big cluster. It still has fairly large holes because, you know, we're only slightly above the critical point, but you can see that the structure of the cluster here is completely different to the one at criticality. Okay, so here is a similar video in 3 dimensions. So here we're doing percolation on a 3D box, and the cluster that's being plotted is just everything that's touching the left boundary of the box. Okay, so you should see as, yeah, okay, so that very suddenly got much bigger, and now it's filling the whole box. Okay, and we'll see this once again with a smaller lattice spacing in a second. So you'll see again that around the critical point, so which is, you see is a line here, so we're getting to it now. You see this very interesting fractal-like geometry at the clusters, which is then going to fill in as we get significantly above PC, and we'll see something that's more like a perturbation of the normal 3D grid. Okay, so hopefully you agree from looking at these videos that there are interesting phenomena to understand here. Okay, whether we can understand them or not is another matter, of course. So how are we going to study these things? Well, you know, as I said, eventually what we would ideally like to do is have some theory of saying, okay, well, if you set P exactly to PC and take a limit, you get some kind of random fractal that you can describe in some way. Okay, let's be a bit more, let's aim for something a bit weaker for now, which is, well, actually the first question, which I won't talk about too much, but it is a very basic question as well. It might be that actually, you know, when you're at the critical point, of course, this is not what you see in the simulations, but it may be that when you're at the critical point, never mind. Maybe at PC you just already have this infinite cluster, so maybe you just don't have any of this fractal geometry, you know, maybe, and this is what we would call a discontinuous phase transition, where sort of you discontinuously move from the having only small things to already having like a linear size thing at the critical point. That kind of thing does happen for some systems, and in fact, it's the kind of thing that happens in the systems that describe like boiling water and things like that. But we don't expect it to happen for percolation. It's certainly not what you see in the simulations. But this is an open problem, especially in dimensions 3, 4, 5, and 6. Okay, now the talk, well, like the emphasis of what I'd like to continue talking about is less about this qualitative question. It's more about the quantitative question of, okay, once, let's say we know that there are only finite clusters, can we describe their fractal geometry somehow? Okay, and one way that we like to study that kind of fractality is via what we call critical exponents. So basically what this means is that if you have some interesting quantity, and it's either you're exactly at criticality and there's something that decays, like for example, the probability the cluster at the origin is large, or you're slightly away from criticality and you have some interesting quantity that either goes to 0 or to infinity as you approach PC. Basically, for many interesting things, we expect them to be governed by some kind of power law. Okay, and ultimately the exponents in these power laws are going to be related to sort of fractal dimensions in the limit, but it's something we can think about just trying to understand these kind of critical exponents rather than necessarily understanding the scaling limits yet. Okay, so one case, of course, where you can understand this very easily is for percolation on a tree. So percolation on a tree is basically just the same thing as a branching process, which I told you about in detail earlier. And you can compute all of these exponents. So for example, if you're slightly above criticality, then the probability, if you're epsilon above criticality, the probability that the origin is an infinite cluster is like epsilon, or epsilon to the 1, if you like. If you're at criticality, the probability the origin is in a large cluster size at least n, decays like 1 over root n. And the expected size of the cluster blows up like 1 over epsilon as you approach criticality from below. Okay, so these are all quite like simple values of these exponents that, again, you could easily do this in an undergrad course if you wanted to. Okay, so what are the conjectures for Euclidean lattices? Okay, so again, as I said, the dimension is going to be extremely important. And in fact, let's read this slide starting from the bottom. So as I said, high dimensions turns out to be easier in various senses. And part of the reason it's easier is that in sufficiently high dimensions, you go back to having exactly the same exponents as the branching process does. These are also the same exponents you get on the Erdős-Rényi graph. Okay, so in particular, all of these things are the same. They all have these simple values. And these are often called the mean field values, which the terminology comes from an analogy with these models of magnetism. It doesn't really make sense for percolation, but still, generally this phenomena that once you get to high enough dimensions, the model on the lattice starts behaving the same as the model on the tree or the complete graph. In other words, as the things with no geometry, this is known as mean field critical behavior. And, one surprising thing, you might, if you thought about it for a bit, you might think, well, okay, it's plausible that like as the dimension converges to infinity, the exponents like converge to their infinite dimensional like mean field values, but which is true, of course, but the much stronger thing is true that they actually fixate at those values once the dimension is large enough. Okay, and this phenomenon is something that you see across all these different statistical mechanics models, although what's called the upper critical dimension, which is when this kicks in, this does depend on the model. So for percolation, it's 6. So if the dimension is larger than 6, you get mean field behavior. For many other models, it's 4. And, it can be anything, I guess. So mean field behavior was proven for high-dimensional percolation by Hara and Slade in 1990 using a technique called the lace expansion. And, in fact, if you look at what they really proved is just that if D is sufficiently large, then it works. So the lace expansion requires some small parameters, and morally it gets down to 6, which is optimal, but it works down to 6 provided that you're happy changing the graph. So working with if you don't care about necessarily proving things for the standard hypercubic grid, but you're willing to look at a different d-dimensional grid, then their methods work all the way down to the optimal case of 6 dimensions. Okay, so that's the high dimensional case. And one way you should think about this is basically once the dimension becomes large enough, the space is so spacious that the model does not feel that it's in a finite dimensional space. It starts just behaving the same as if there was no geometry at all. Okay. Now, in low dimensions, it's really different. You really do strongly feel the effect of being in finite dimensional space. And in 2 dimensions, what happens, it turns out, is that all of these critical exponents have these kind of rational but strange values, right? Like 5/36, 5/91, etc. Okay. Now, the reason why, and again, this is quite typical for 2 dimensions in that also for many other models, you get these kind of weird rational values that you can exactly compute. They're kind of complicated, but you can compute them. And this ultimately, is related to many very deep things like the connections with conformal field theory and so on that I don't have time to talk about. But this is a very 2-dimensional phenomenon. I should say, as it stands, we can actually prove all of these things for this one particular case of site percolation on the triangular lattice, which is the thing I was actually showing you the simulation of, where as the culmination of important work by many people. Okay. So what about dimensions 3 through 6? Well, basically what we expect is that whenever the dimension is strictly smaller than 6, you get exponents that are different than the high dimensional ones. But in dimensions 3, 4, and 5, they're probably very difficult to understand. So, we don't expect them to have rational values, and they'll probably have transcendental values. Even physicists who are allowed to use non-rigorous methods, the best they can do is maybe, estimate these to some number of decimal places. They don't conjecture any exact values for these exponents. And I should say, it's also very hard as a mathematician to even just prove that these exponents are well defined. I mean, that's something that we certainly don't know for these intermediate dimensional models. Now, one interesting case where we do have conjectures, but we don't yet have theorems, is the 6-dimensional case. So again, 6 is the upper critical dimension. So it's exactly the boundary for when you should begin to have this simple behavior. And what we expect, and again, this is something where similar things happen across many models, is that you'll almost have this high dimensional behavior. In fact, the exponents will be the same, but you'll have some logs. Okay. And in the case of 6-dimensional percolation, there are precise conjectures about this, where, for example, if you look at the probability that the cluster at the origin has size at least n, it should be in high dimensions, it's 1/√n. In 6 dimensions, it should be larger by a factor of log n to the 2/7. Okay. And actually, you can see that all the things I wrote on this slide have this 2/7, but that's just because I picked poorly which ones to show you. Actually, if you look at other quantities that are interesting, you can see different powers of log that are not 2/7. So for example, if you look at the probability 2 points are connected to each other at criticality, so in high dimensions, this decays like the Green's function, so the distance to the -d+2. In 6 dimensions, conjecturally, it's larger than that by a factor of log of the distance to the 1/21, which is, of course, an extremely slow growing function, but it should be there. One thing about these log corrections is that you don't expect these to actually change what the continuum limit is. It should just change how you have to scale to get the right continuum limit. So in 6 dimensions, whatever these limits are, you expect to get the same ones in 6 dimensions as in high dimensions. Whereas when you go below 6 dimensions, you should really have a very different theory of what the continuum limit is. Okay. So one way you can think about this distinction for percolation is that, when you look at a really big cluster, like you look at the cluster at the origin and you condition it to be extremely large, in high dimensions, it will basically look like this continuum random tree again. Okay, so the cluster is not a tree, right? It contains cycles all over the place, but they're not important in high dimensions for the macroscopic geometry of a large cluster. It looks basically like a tree. Whereas in low dimensions, that's not the case anymore. The cycles are really important macroscopically, like you see cycles, macroscopic cycles of the same diameter as the cluster. And this is kind of what's driving, in some sense, it's what's driving the distinction between low and high dimensions. Okay, I think I'm already running low on time, so let me skip ahead a bit. And I should say, one thing of this high dimensional story is that there is actually you can take a continuum limit of the percolation model, and it's something called super Brownian motion, which is like the limit of, you take this continuum random tree and then you embed it into space using Brownian motion. And this ends up giving you 4-dimensional objects in space. Anyway. So maybe just to say one more thing, in 2 dimensions, again, this is something that's quite well understood, and there's this whole theory of conformal invariant scaling limits, SLE, blah, blah, blah. And one really remarkable outcome of this is that we can say exactly what, in this picture I had before with this fractal clusters in the hexagonal lattice, the dimension of these in the limit is exactly 91/48, which is just completely bizarre, but it's the truth. This is something that comes out of all this SLE theory. And maybe, I'll just end on this slide because I know when I give this talk that I don't say anything about my own work, but just to say something in the last 10 seconds, I think this problem of understanding models in intermediate dimensions it's kind of a problem for our times, if you like. The previous generations made a lot of progress on 2D and high D, and I think this is really something, where I hope we'll see a lot of progress over the next century, actually understanding critical phenomena in intermediate dimensions. So one thing I've been trying to do is to say, okay, well, you have to carve out some problem you can actually solve, right? I mean, there's no point just doing something that's hopeless. So we have to say, okay, what's like the simplest problem that gets towards this, but we can do something. So one thing I've been working on a lot recently is with what are called long-range models. And there's been a lot of exciting progress recently where for these models, there are some aspects of their critical behavior that we can actually understand in intermediate dimensions. Anyway, I'm over time, so I'll stop there. And thank you all again for your attention.
Thank you, Tom, for this very interesting lecture. And obviously, it has many applications in real life. So are there any questions for Tom? So, okay. If you have any questions, please, you can ask.
Maybe I can start with a simple question, Tom, because I've worked on some clustering, but in machine learning. So I have concern on what is a cluster for you, that like the definition, because if I understood well, I don't know, because when you put the example of the basic application in the percolation, you said that it was any connected set of edges. But for instance, in the Erdős graph or in the tree, I don't know what is a cluster for you.
Right. So I guess, it's right. It is just a connected component. So in the Erdős-Rényi random graph, it is still just the connected components. In the tree, you can think there's only one cluster. You're only looking at a single cluster when you do the branching process.
Okay.
So you can think like the branching process is actually something you see in the limit of Erdős-Rényi if you just explore the cluster at the origin, it will look at small scales like a Poisson branching process.
Okay, great.
So the tree is sort of only one cluster. It's quite. I think it's unrelated to the kind of clustering people do.
Yeah.
Statistics, which is more, yeah.
Yeah, because I was looking at where are the clusters. I can just see, one connected graph, and that's all. Yeah, so
yeah,
I
was
didn't
only
know
showing
you
one
were.
in the picture.
Okay.
Yeah.
Okay, thank you.
But I should say for these theorems about the scaling limit of Erdős-Rényi, they really tell you about the joint scaling limit of all the clusters together. I was only showing you pictures of one of them.
Okay, thank you.
Thank you. Are there maybe any other questions? Then, if not, thank you all for coming. Thank you, Tom, for accepting to have this talk. And I hope we will see all of you on the following seminar, which will be on first Thursday, but in April. Christina, do you have something to add?
No, you are welcome to come again. Thank you, Tom, for your time.
Yeah, thank you for having me.
Thank you. Then bye, we can finish.
Tom, I have a question for you, because when you were talking about phase transitions, it reminds me on the concept of chaos, no? Like a chaotic system, right? Because, well, I don't know. It has some. I don't know if it has some.
Yeah. Well, I guess there are things you would often want to prove about these systems, which I guess have kind of the flavor of the chaos. I guess I think of chaos as being some kind of mixing in time. And often to study these systems, you need to prove like mixing in space. So you might want to say, if you take the picture on one scale and then you zoom in, you should see something that's roughly independent of what you saw at the big scale, which is it's kind of a chaotic type behavior under scaling rather than under time evolution.
Okay.
Although people also look at the time varying version, like dynamical versions, in other words. So you could study, for example, dynamical percolation. In fact, I imagine Niels probably has some nice videos of that on his YouTube channel. And so there you can prove people study this. They don't normally call it chaos, but they could do. People who work in that area normally call it noise sensitivity. So the idea is that if you take your critical percolation configuration and then you noise it, so you re-randomize like an epsilon fraction of the edges or something, then this completely changes the macroscopic picture. So even though you only changed a very small number of the edges, if you're interested in what the clusters look like on the large scale, it completely changes. And this is something, again, people can understand in extraordinary amounts of detail in 2 dimensions. So in fact, there are even full scaling limits constructed of like what is the continuum. So you have to scale the noise in the right way where you still see the dependence. There's another exponent basically that for a system of size n, you should noise with epsilon is some power of n to see the geometry changes a bit but not completely, and people can understand all that stuff completely, basically in 2 dimensions. But
okay, interesting.